Okay, let's move to the few applications of using diodes. So one application would be a kind of clipping circuit. So clipping circuit. So before moving to this clippers or clipping circuit, or in some textbooks seems simply explain it as limiters. So we basically discuss three types of diode models. One is ideal, so the other one is like a simplified model. So the third one is piecewise linear model. So as we discussed last time, these two are kind of a common type of models which we can use for the analysis of diode circuits. So the ideal model and the simplified model. So then we'll consider a very simple diode circuit. So this is a very simple diode circuit. So you have a resistor and you have a diode here, and so the voltage across the diode is considered or measured as the output voltage, and this is your input voltage, a kind of a sinusoid. This is your VE. So you have a resistor. So you are asked to evaluate the output voltage. To make this analysis simple, we'll always stick into the ideal model. So assume that the diode is an ideal one. Okay. So for the simplicity, so we'll stick into this ideal diode model. So for the ideal diode model, so if the diode is forward bias, the voltage across the diode should be greater than or equal to 0. If it is reverse bias, so the diode voltage should be less than 0. So forward bias case, we can replace the diode with a short circuit element, and for reverse bias case we can simply replace the diode with the open circuit element. Okay, so then by sticking into this ideal model, we'll try to analyze the circuit here. So first thing, so we need to find the actual voltage across the diode. Why we need to find the actual voltage across the diode? We then, based on the voltage appear across this diode terminal, we can simply identify or recognize whether the diode is a forward bias one or a reverse bias one. So we can simply identify the states of the diode, whether it's forward or reverse, based on the actual voltage appear across the diode. So to evaluate the voltage drop across the diode, first we remove the diode and measure the open circuit voltage. So then it would be something like that. So here it should be minus and plus. So this is the open circuit voltage, and this is your resistor, and this is the input voltage. Okay. So then by apply Kirchhoff voltage law KVL, so we know that if it is open, so there won't be any current flow through the resistor. So the open circuit voltage across these two terminals should be equals to VI, or the input voltage. So from this we can simply say that then the diode voltage equals to the open circuit voltage appear across these two terminals, which is equals to VI. So this is the conclusion we made for this circuit. So then to make diode forward bias, we know that the voltage drop across the diode should be greater than or equals to 0. So this is the condition that diode should meet. Diode should meet. So then from this one we can easily evaluate a condition where this particular circuit should satisfy to make this diode forward bias. So once you substitute it here, so you can simply identify that Vi should be greater than or equal to 0. Okay, so this is the condition that in this particular circuit, the circuit should manage to make this diode forward bias. If the input voltage is greater than or equal to 0, so then this diode become forward bias. Similarly, to make this diode, to make the reverse bias, we know that input voltage should be 0. Okay. So then we can separately analyze. Okay, so then we'll draw the input signal. So this is your input signal. So this is Vi. So during this region, Vi greater than or equal 0, and then we can simply claim that diode should be forward. So during this region, so your input voltage is less than 0, then your diode should be reverse bias. So then we basically identify when and where this diode get forward and reverse bias. So then we can analyze the circuit for the forward bias condition and for the reverse bias condition. So for the forward bias condition, we know that diode can be replaced using a short circuit element. So then this circuit becomes like this. So this is the diode. So we know that if the diode is forward bias, then the circuit is simplifies to this. So this diode can be replaced using a short circuit element. So then we have short circuit element. So what about Vout? Vout is simply 0 because it's the voltage drop across the diode. So then we can simply claim that during this forward bias region, the output voltage is 0. So then, so we'll see. So we'll see what happens for this reverse bias scenario. So we know that if the diode is reverse bias, we can replace the diode with open circuit element. So then the circuit simplifies to this. This is open circuit and this is your output voltage. So this is open. So once you connect this is open, so there won't be any current flow through this resistor because this is open circuit. So then here V out should be equals to V. So then we identify that that is forward bias when the input voltage is greater than 0. So then we found that the output voltage is simply 0. So again then we found that when this input voltage is less than 0, that would get reverse bias. So during that period we found that the output voltage is simply equals to the input voltage. So this is something like that. So it simplifies all the input voltage. So this is the output for this particular circuit when we stick into the ideal diode model. So we'll see what happens if we stick into the simplified model. So we have resistor here, a diode here, and this is your input Vi. So this is your output R and a diode. So now the simplified model. So then we basically consider the barrier voltage also into account and we stick into the simplified diode model. So for this case, we know that if the diode is forward bias, so the diode voltage or the voltage drop across the diode should be greater than or equals to knee voltage. If it is reverse bias, we know that the diode voltage should be less than Vk. Okay. So then from the previous we can easily get that the diode voltage should be equals to input voltage for this particular circuit, for this circuit. So based on these two conditions we can simply identify two regions. If the diode is forward bias, we know that diode drop should be greater than or equals to Vk. So once you plug this, we can easily say that your input voltage should be greater than or equals to Vk to make it forward. So this is the condition that circuit should maintain to make this diode forward bias. Similarly, you can find the condition to make this diode reverse. So then your input less than VT. So these are the two conditions that circuit needs to maintain to make this diode forward bias and reverse bias respectively. So then we'll draw the input circuit, input signal, because now we know that the diode switching is simply happens based on the diode input. See, so here Vi should be greater than or equals to Vk. Here Vi should be less than Vk, which means like so the diode switching or the state of the diode should be completely depend on the input circuit. So we'll identify, so this is the new voltage, so this is the input voltage, so this is your input voltage Vi. So we'll try to identify these two regions. So Vi should be greater than or equals to Vk to make this diode forward bias. So this is the region where you can find your input is simply greater than or equals to Vk. So during this period your input is greater than or equals to Vk. So it means like this, during this period diode should be forward bias. What about during this? So your input is simply less than Vk, so then that is reverse bias. And even during this small period, so during this block, again your input voltage is less than Vk. So this is again reverse bias. So during these two regions, your input should less than Vk. Here also input should less than Vk. So now we identify the regions where this diode get forward and reversed. So then we'll analyze the circuit and find the output for these two states. So when this diode is forward bias, when this is forward bias, we can simplify the circuit like this. Okay, so we can replace the diode with a fixed DC source of Vk because it's forward bias. So then for this particular case, V out should be equals to Vk. So it's exactly equals to the voltage, the value of the voltage source we connect across these two terminals. So V out should be simply Vk. Okay, so then we can just draw this. So during this forward bias region, output voltage equals to Vk. Okay, so then we'll see what happens to the if this does get reverse bias. If the diode get reverse bias, so we know that we can replace the diode with the open circuit element because it's reverse bias. So then there won't be any current flow through this network. So then the output should be equals to input. So you are just plugging a voltmeter here and there won't be any current flow through this one. So the input resistance of the voltmeter is simply infinite. So then no drop across the resistance, you are just measuring the voltage across the source Vi. So this, so once you draw this one, so during this reverse bias region, the output voltage simply follows the input. So then it's become like this. It's very simple. So then this is the output. So see what happens to the circuit. So during this positive cycle, so the input voltage is simply clipped at Vk. So you can simply get the output voltage as a knee voltage. So it means your input is simply clipped at Vk. Input Vi is clipped at Vk. So this is the thing happen in this positive cycle. So if you place the diode like this to this very simple circuit, so you can clip the positive cycle at the knee voltage of the diode. So for example, if it is a silicon diode, so then we can assume that this is 0.7 volt. So then this basically clips at 0.7 volt. So if it is a germanium one, so this is simply your positive cycle of the input is simply clipped at 0.3 volt. So by introducing this simple diode across the output for this particular circuit, so you can simply clip the input voltage at Vk during this positive cycle. So but during this negative cycle you can simply obtain the input voltage. But if it is the positive cycle, when you place the diode like this, you can simply clip your input signal at Vk. So then see what happens to this circuit. Okay. So now we'll introduce two diodes instead of a single diode. We simply introduce two diodes. Again, you may have the sinusoidal input, and so we have D1 and D2. So by looking at this one, we can model this series diode with a single equivalent diode like this, because the idea here is like to make this. So if you want to flow a current through these two diodes, to make this conductive, to make this conductive, so both D1 and D2 should be forward bias. If one of the diode gets reverse bias, so then you can't see a kind of a current flow. So to make this conductive, so to make this conductive, this D1 and D2 should be forward bias. If either one of this diode get reversed, you can't see a current. So then either one of D1 D2 is reversed, so you can't see current, no current. So then if it is conductive, you can simply identify that it's a kind of a diode, single diode, which has a compacting effect of these two. So if we assume that D1 and D2 are D1 and D2 are similar, so then we can model this equivalent diode. Let's assume D equivalent with a knee voltage of 2 VK, because this introduces a VK drop and this is again introduce a VK drop because they are identical or similar diodes. So then we can replace this with a single equivalent diode having a knee voltage of 2 times VK. Yeah. So then again, like if it is a equivalent diode, so we can think of kind of the actual voltage appear across this entire diode block between these two element no terminals. So we can find the open circuit voltage across A and B by open circuit this, and this is actually equals to the input voltage. So from this one we can claim that VD equivalent, or the diode voltage across this equivalent diode, or the should be equals to input voltage. So then we can again build argument like, so if you want to drive a current through this path, so then both D1 and D2 get forward bias. So then to make this forward bias, so to make this D1 and D2 forward bias, you have to simply make this equivalent diode forward bias. To make this equivalent diode forward bias, we should maintain this condition 2 VK. So if the voltage drop across this equivalent diode is greater than or equals the 2 times the knee voltage, so then the equivalent diode get forward bias. Again we can claim that if this equivalent diode get forward bias means both D1 and D2 gets forward bias. So to make this D1 and D2 forward bias, you have to maintain at least 2 times a VK voltage drop across these diodes. So then only you can make these two diodes forward bias. So then plug in this, we can simply claim that Vi should be greater than or equals to 2 VK to make it forward bias. Similarly, so to make it reverse bias, so your input voltage should be less than 2 VK. So then if you draw the input circuit, so now this is VK and this is 2 VK. This is 2 times VK. So then, like in the previous, this is the region where diode get forward. So during this it's reversed, and during this also it's reverse bias. So if you draw the output, if it is forward bias, so then we know that you can replace this diode with equivalent diode with a fixed DC source of 2 times Vk. So then Vx should be 2 times Vk, and during this reverse region it simply follows the input. So this becomes the output. This is your input and this is the output. So see, now for this case, positive cycle is clipped at 2 Vk. Okay. So once you add another similar type of a diode in series with the previous one, then you can simply clip the positive cycle of the input at 2 times Vk. So what about if you add 3 diodes together? 3 equal diodes. So then you can simply claim that this positive cycle is clipped at 3 times Vk. If you add 4, it becomes 4 times Vk. So if you add a silicon diode and a germanium diode, so this is a silicon and this is a germanium. So this adds a zero point 0.7 voltage, this adds a zero point 0.3 voltage. So all together we can replace these two diodes with the equivalent diode with an E voltage of 1 volt. This plus this. So then this input is simply clipped at the value of 1 volt. Okay. So then by introducing this series of diodes, you can simply clip the input at a given value based on or depending on the barrier voltage of diodes. Okay. So if you change the orientation or the direction of this diode, so if you change the direction of the diode to this, so then you can see this kind of output. So this is simply fast and this is clipped at minus Vk. So if you introduce another diode in series with that, so it should goes to minus 2 Vk. Minus 2 Vk. So likewise. So if you make it a kind of summary, if you have this kind of a diode, you will see this kind of a output. If you change the orientation of the diode, so you will see this kind of output. So the difference is, in this case you input positive half cycle is simply clipped at Vk. If you change the orientation of the diode, your negative cycle is simply clipped at minus Vk. So this is the difference. So this is the very simple clipping circuit. So what happens if you add these two diodes together? So if we add two diodes together, so then what happens to the circuit? So we can similarly argue, so this is, if this is your input, so we know that with this orientation, if D1 is forward bias, definitely D2 should be reverse bias. So then during this D1 conductive, so when this D1 get forward bias, D2 is reverse bias, so we can simply replace this D2 with the open circuit. So then this is basically simplified to this kind of a scenario. So it's basically this. So if this D2 gets forward bias, so we know that D1 is definitely reverse bias because of this orientation of these two diodes. So then it should be something like that. So this is simply aligned with this one. So then what would be the output? So we know that, so this arrangement triggered for the positive cycles, this diode. So D2 is the affecting entity for the positive side. This is the scenario where your positive cycle get affected. So this is the scenario where your negative cycle gets affected. So then during this positive cycle, you have this kind of a circuit will be there, or this whole circuit can be simplified to this model. So D2 get forward bias and D1 get reverse bias, and it simply match with this one. So then the positive cycle of the input should be clipped at Vk. So then during the negative cycle, so it simply align to this circuit. So like here. So then this negative cycle is simply clipped at Vk minus Vk. So it's minus Vk. This is minus Vk. This is plus Vk. So during this other regions, we know that both diodes get reversed because the input voltage is not sufficient to make either one is forward bias. So then this, so by adding this kind of a diode arrangement, so you can keep these both cycles at Vk. So again, like by introducing series set of diodes, you can adjust these clipping voltage. So for example, if you add another diode here, so then this should move to 2Vk, and negative cycle is simply clipped at minus Vk. If you add another diode to this one, again your negative cycle is also clipped at 2 times minus Vk. So likewise you can adjust the, or you can introduce whatever the number of diodes to this, either branch 1 or branch 2. You can adjust the clipping level of the input voltage. So this is the very simple clipping circuit. This is very simple clipping circuit. So we'll discuss a little bit complicated versions during the next couple of videos. So this is basically the a very simple clipping circuit, so you can obtain the output, or you can analyze the circuit using the theories which we discussed previously. So if you want to analyze a circuit, first you should stick into either ideal model or simplified model, which are the very commonly used models. So then depending on these models, you can simply, so initially you have to identify the actual voltage appear across this diode by make this diode open circuit, or remove the diode and evaluate the open circuit voltage across these two terminals. So then this is the open circuit voltage, and it's again the actual voltage appear across the diode. So based on this actual voltage appear across the diode, you can find whether the diode is forward bias or reverse bias. So based on that, you can simply identify the switching regions of the diode with respect to input signal. So whether this diode is forward or reverse based on the input signal. So then you can analyze the circuit for these two different state scenarios. When this diode get forward bias, you can simplify the circuit using appropriate replacement for the diode. If it is ideal, you can simply replace it with the short circuit element. If it is a simplified model, you can replace the diode with a fixed DC source of value of Vk. So if it is reverse bias, you can simply replace this diode with open circuit element for the ideal model as well as the simplified model. So then you can simply obtain the equation for the output voltage by analyzing the circuit, because no diodes are there. So you have resistors, sources, and either short circuit or open circuit elements in the circuit. So you can easily find the output voltage for the simplified version. So then you can just draw the input and identify the regions, and based on this region you can analyze the circuit and find out the output voltage. So then we can simply draw the output voltage on top of the input voltage. So draw the output voltage. So this is the input voltage, so you can simply overlay the output voltage on the input voltage. So this is the very simple briefing about the clipping circuit. So we'll next time discuss little bit complicated circuits and how try to identify or try to get an idea how to get the output voltage and how the circuit behaves like this.